All right, good afternoon. So we finally got the technical glitch resolved. So now I can write here, and then you'll see here. And so we use a software, so record it, and with the voice and the image. So then we'll post it again. So this will be better quality images when you watch on YouTube. All right. Okay, so last time we talked about actually loaded members. So we just call it a bar or a cable, right? Or it can be a wire. In reality, it can be just a rigid bar, right? So or it can be, as long as it's actually loaded. So you have one dimension with slim, long bars that under actual load. That's the situation we talk about. Okay. So we came up with one simple equation to calculate how much deformation you're going to get if you apply the load. If you apply the load to a bar, right? Say you have a bar here, and with the length L, cross-sectional area A, and the material is E. So you apply a load here. Okay. So the equation of elongation. Anyone remember that equation? PL over EA, right? So that's basically the simple equation that we can calculate how much elongation you're going to get, right? But this is a very simple situation, but just you need to just get a sense of how things change when you change one of these parameters, right? Let's say if I need to build a cable, I need a cable to support one person initially. Now I want to support two person. So make sure you select double the cable instead of using a longer cable, right? So that's kind of a common sense. Hope you can build it into your judgment, all right? So now, today we're going to talk about a little bit complicated situation. That is when you have a non-uniform bar. At the end of last class, we talked about this situation. If you have a bar, let me make the pen a little bit smaller. Okay, if you have a bar here, right, it will be elongate. Okay, hold a second. Let me twist this. I can put it down. Give me 1 second. Oh, I need to change it back. This gadget is supposed to be changing their own direction. All right. Okay, so, all right, then I need to go back. All right. Okay, I'll work it out next time. Don't want to waste your time waiting here. Okay, so we have this. All right. Okay, so last time we talked about if you have a bar like this, but somehow there is a hole in the middle of the bar, right? So if there is a hole here, and then this bar we said will be not uniform, right? So you have to divide it into several pieces, calculate their elongation individually, then put them together, right? So the general idea is very simple. For any non-uniform bars, okay, you divide it up. Okay, I use the word divide. I'll tell you why I quote it. So divide up into several pieces, right? And then you calculate each one, all these individual elongations, and then you add them together. That give you the total, right? That's how we're going to do it. So that's the general idea. Right? So today we're going to go over quite a few examples, say all different kind of variation of non-uniform bars, and how can you use this equation to solve it, all right? So the first example I want to point out is this situation. Okay, let's say I have a bar, right? There will be different this portion versus this portion. Okay, excuse my drawing. The line are not so straight. Next time I'll maybe change to something, draw it in advance, so you will see a better drawing. All right. So you have a bar like this one. Okay. So the two parts, they're different. So this part you have A1, and the material maybe E1, right? So the length here is L1. This part, you have different cross-section. The material can be the same or maybe different. So in general, you may have different material, and the length will be L2. Now for this one, how can we calculate the total elongation? That's the question. You do them separately, right? We all know this idea. So that's the right direction. So we do it separately. Okay, so separate, where you cut it, separate them, or divide them. You divide here, right? So you say this is bar 1, and this part is bar 2. So you divide them up. Okay, I use the word divide. Okay, now once I divide it up, now I have two pieces. I need to find the elongation of each one. Okay, how can I find the elongation of, let's say, piece 1, number piece 1? You need to draw a free body diagram. Figure out what's, say here, this equation we have, right, is applying to uniform situation. So you just need to find out for that piece, what's the load there, what's the length there, what's the material constant there, and what's the cross-sectional area there, right? So you have to find each of this. Okay, all the three things are given, except the load. We don't know the load here in segment 1, and the load in segment 2. So that's the only thing we need to find out, right? Because we'll know all the A1, E1, L1, all these parameters. So we just need to find out what's the N1. So let's say in this piece, what's the force N1 here? In this piece, what's the force N2 here? Right? That's all we need. Okay, how can we find this internal force, N1, N2? Make a cut, right? So here's the keyword, cut. Okay, so it's different from dividing. Okay, why is different? In English, maybe not different, right? I'm trying to use two different words to remind you, when you make a cut, all right, you don't make a cut here in the dividing point, this between the two segments. You always cut in the middle of the segment that you're looking for. Okay, so let's say here, N1. So I made a cut here, right? So this part, I cut N1. And then this is the N2 cut. So if I look at the N1 first, so I can draw, this is the cut. So I can draw free body diagram, right? So I can select the segment from the left or right. I can draw it. Either one. Okay, so you can draw both, actually, right? But let's say we pick the one from the right. Okay, so if I draw everything on the right, so that's what I get. So let me change the plane back to black. And then, so this is what you get. So this part, I'm just put it parallel to the top there. You can see it. So this is the second part. Right? So that's the piece I get, free body. Now I need to draw free body diagram. So I need to label all the load. So this is the load here. Anything else? The reaction. The reaction here, N1. That's what I'm looking for. That's why I made a cut here. Because this way, N1 show up. So I can write equation about it, and I can find it. Okay, so I have equation of equilibrium. I can use to solve this problem, find out N1, right, based on this free body diagram. All right? Okay, so have you write down your equation of equilibrium? Yes, so you have what? You have minus N1 plus P equals 0, right? Okay, so what's N1? Equal to P, right? If P is 10 Newton, N1 will be 10 Newton. Okay, so now, okay, the question is, okay, does it matter where I actually made the cut in the segment? What if I made a cut, let's say use a green one. Say, what if, oh, it doesn't work. So if I made a cut here, so I'll draw a free body somehow just this part, right? Just the one on the right. Right? You still write the same equation. So your force will be the same, right? So in other words, it really doesn't matter if for this uniform segment where you actually made the cut, right? So therefore, you always can make anywhere in between this segment. So here's my recommendation. Always make a cut in the middle. Just easy to draw, okay? And one thing is never make a cut here. Okay, the transition where you dividing the segment, don't make a cut right there. Okay, what's the reason? The reason is there make the things complicated. You don't know what's the first there. Okay, this example is actually not that clear. But your next example, you will see clearly you will never make a cut with the dividing point. You always make it between the segment, in the middle segment. So you either the red or the blue here. Right? Okay, actually it doesn't matter. Where in this blue or red give you the same answer. All right, so we know N1. Now can we find out N2? N2 the same. So we already made the cut here, right? So the cut is here. So I'm just drawing copy from the top. And then you have this small segment here. And load P is here. And so this N2 will show up here. Right. Now, what's N2? You do the same, right? Write the equation of equilibrium. And then find out the N2. For this one, so easy, right? So you don't actually, you can skip the next step. But actually, I still recommend you write down. Just follow the fixed step. That's make your problem-solving procedure kind of stand. Easy to avoid mistake. So you do the same. So you write equation of equilibrium, and you have N2 plus P equals 0. And you find out the N2. Okay, now, you know N1, N2. Now, can you find the delta 1, delta 2? Yes, so we can write, okay, delta 1 will equal to N1, L1, E1, A1, right? And then delta 2 will be equal to N2, L2, and E2, A2, right? Now, can you find the total elongation? You just add them together, right? It's just a summation, simple summation. Put them together, then you find it. Okay, now, can you find the stress in these two segments? What kind of stress you will have? Normal stress, because it's normal force, axial tension, normal to the cross-section. All right, so you're going to have sigma 1, that is N1 over A1. And then you're going to have sigma 2, that is N2 over A2. Right? Okay, so now, can you find the maximum stress in this bar, in this whole segment, whole structure? What's the maximum stress? Whatever the biggest one of these two, right? Okay, so here is sometimes people make a mistake. I ask you what's the largest. It's like I ask you who is the tallest. So you just pick one person, whoever is the tallest, right? You can never add two people's height together. Give me that's the highest one. The same here. Okay, so stress in the left bar 1 is sigma 1. The stress in the right segment 2 is sigma 2. So the maximum will be the one of this. You pick the biggest value, right? So you can never add them together. Say this is the maximum, and I do see that in my exam questions. So make sure everyone here today don't put it that way, because maximum is a maximum. You pick the one of the maximum, right? Okay. Any questions so far for this problem? Yeah, you calculate their values, right? Let's say one is 20, one is 30, then the 30 will be maximum.
So is it safe to say by inspection that it's going to be sigma 2?
Say that again?
Is it safe to say by inspection that it's going to be the second section?
Yeah, by intuition you can tell why. Because you know from here that A2 looks like smaller, right? They have the same force. N1 and N2 actually equal. But the area is different. So wherever the nearest, smallest area, there will be higher stress. See, that's the intuition, right? So with that, without number, you can quickly make a judgment, right? So you don't actually, in this case, you don't need a calculator. You just quickly answer me, oh, this is the smallest cross-section, that's the biggest one, right? So lots of problems, actually, you can do without really use a calculator. So that's why you need to build up this intuition, this common sense, and that actually help you judge your answers. All right. Okay, any other questions? Okay, if not, let's look at the next example here. So I have this a bar, right? So I make it easier. So I have the constant cross-sectional area. Everything is the same. So you have this A, L, and E material. Everything is the same. Right? But I have a load P1 applied here. Let's say we give a value. P1 equals to 10. How about 10? We like 10, right? So 10 Newton. All right, but for this bar, somehow I need to carry 2 loads. So there is another load here. All right, we need to give a value. Say another load, make it a little bit complicated, so I'll put it this way. So there is another load, I call it P2, that equals to, let's say, 4. All right. Now, what I'm looking for is, okay, for this bar, how much are you going to elongate? And what's the stress, maximum stress there? Then I can check if it's safe or not, right? Okay, so how can we find out the elongation of this bar? First, is this one a uniform bar? Can we use that simple equation at the top, just one simple equation? So we have the equation here, right? See, right here. Okay, this equation, I just squared it. Okay, this equation, when can you use this equation? Uniform bar. Okay. So uniform bar, what's that mean by uniform bar? That means all these parameters, P should be the same everywhere. L is the total length. And then E is the same everywhere. A is the same everywhere. Now, look at our situation here. Okay. A is the same everywhere. L is the total length. Material is the same everywhere, right? It's all E. Now, is the load the same everywhere? No. So the answer is no. Therefore, we cannot just use that equation to calculate. Right? So this one is a non-uniform bar. Right? So in other words, okay, you can put a note here. So non-uniform means there are 3 types. Okay, so non-uniform. There can be multiple way of non-uniform. One is you have the area A, non-uniform. The second, you can have material non-uniform. Right? That's the example we just had. And also, you can have the force N, non-uniform. And the most challenging question, people make lots of mistakes, is actually the third one, when the force is not uniform. Right? So we're going to actually go over a couple of examples, and I'm going to give you a quiz related to this. Ask you to judge what's the force in each segment when their situation kind of complicated. Right? Because this is the most common part that people make mistakes. All right, so let's go over this example first. Then you can see what I mean there. Okay, so now we know this is a non-uniform segment. Right? So we have to divide it up. Okay, where to divide it? Looks like it should be somewhere here. Let me use the blue one. So should be somewhere here. That's the difference, dividing line. On the left, same as everything uniform. There is nothing kind of interferent or applying to it in the middle, right? Between this point A and point B, point C. So between B and C, there's no other force. Between A and B, there's no other force. So point B is a natural dividing line. So we'll divide this one segment into 2 separate segments at B. That's the first step. Okay, now next question will be, what's the force in this part? What's the N1? What's the force in this part? N2. So we need that, right? Because we know it's a 2 separate segments. So we have to find out N1 here, N2 here, then we can use the equation separately and then put them together. That's still the same logic we're following. Okay, now how can we find N1, N2? Make a cut. So again, so the word is first make a cut. Right? Then you draw the free body diagram. Right? Then you write the equation of equilibrium. Right? And then what's next? Then you calculate the deformation, right? Or deformation or elongation. Okay. So I summarize this step in what I call it FED. Free body diagram, equation of equilibrium, then calculate deformation. So basically 3 equations, 3 things. You combine together, you can solve all the type of problem. All right. So I first made this, just give you this general suggestion. Okay, so use the word FED. All right. Now let's follow the step. So first thing, the F part. So you have to cut. Okay, to make a cut, we already did here, showing in red. That's the cut. Okay, now we need to draw the free body diagram. Okay, so which one we want to draw first? Okay, so let's say we want first, I think I can use this one. We want to draw this part. This is the whole thing, right? I'll draw this whole segment. So I'll do it here. Okay, so we'll draw the line. Actually, it will be easier if you have paper still going on. I can go next page. Let me see. I can get to the next page. Okay. Go back to home. Where is it? Okay, give me 1 second. Let me get to this page going. Insert, maybe insert. New page. Insert. Okay, here, page break. Okay, so I insert break. But somehow it's going up here, so I'll just continue at the top. Okay, so I'll make the first free body diagram. So let's go back here. Right. So this is the red. So that's the cut I made here. So this will be the N1 I'm looking for part. So then, okay, so this is the part. I'm drawing the right part, right side. Okay, so here's the point B. Here's the point C. I'm just copy that part, right? You can just follow it, put it underneath your paper there. Okay, so then this will be the N1 I'm looking for, right? And this is a complete free body diagram? No, I miss all the load, so I have to label all the load. So the load I have will be P1 here, that's 10 Newton. And then I have 4 Newton here, P2. Right, that's 4. And this is 10. So we know all these values. So this is a complete free body diagram. Okay, so that's the F part. We're done. So the first is the F part. Now we need the E part, equation of equilibrium. How do you write the equation of equilibrium about this one? All the forces together should be 0, right? That's the equation of equilibrium for this one. Because everything in one direction. Of course, everything, sigma Fy should also be 0. That's automatically satisfied. Right? Okay, sigma Fx should be 0. Now, translate into this situation here. What will you have in this equation? So you have minus N1, that's good, minus N1, and then you have minus P2, that's a 4, right? And then plus P1 equals 0. Okay, so we know all the values. Now can we jump one step, say, okay, what's N1 value? It's 6, right? Negative or positive? It's positive. See here, negative N1, negative 4 plus 10 equals 0. So therefore, N1 must be positive 6. That means what I assume this way is correct. Okay, which way? The pulling way. So it's a positive tension, right? So that's positive. So when I don't know it, I always assume it's tension. I just label it away from the surface. If I don't know what the value should be, before I make any judgment, I'll always assume it's positive. So it's always away from the surface. Okay, in this case, I assumed correct, and it's actually gave me a positive 6. All right, so we find out N1. Now we can calculate the deformation in this one, right? Okay, now what about the other segment, this part? So we need to draw the other free body diagram, right? If I made the cut here, I need to find out N2, right? So draw it here. So I just draw this segment. And then this is still point C. So you have this load P1 here. and then this will be reaction N2. Right? This is complete? Yeah, so that's it. There's no other force. What about P1? When I make this cut, does P1 apply on this piece? No. P1 applying on point B. Right? I'm not looking at point B. Right? Yeah, P2 doesn't apply. Yeah. Oh, I said, okay, sorry. I said P1, right? Okay. Yeah, P2 doesn't apply. I scare you, right? Okay, so P1 definitely at point C, it's there, right? The part that P2 is applying point B. So I made a cut here, only this portion. So P1 don't show up because the application action point is not there. So I should not plot P2 in this diagram. Okay, so that's complete. Now, what's the equation of equilibrium? So it'll be sigma fx equals 0, right? So you have negative N2 plus P1 equals 0. So what's N2? N2 is 10. All right? N2 is positive 10, right? Yeah, so I assume its tension is correct. So it's actually tension. Right? Okay, this actually you can use common sense to judge. Because P1, someone is pulling there. If you stand right at this point, this red point here, if someone stretch your arm, what do you feel? You'll feel tension, right? It's like the two of you stand in line. Okay, you're just stretching each other, and then one person stretches to the wall, holding the wall. Then if someone pulling here, then you're the first person, you'll feel tension. Now, if you're the second person here, you'll feel, okay, the wall is pulling you here. And then on this side, okay, there will be P1 and P2. They all pulling on you. But the effect will be they add together. So they cancel a little bit out because P1 is pulling, it's like you're holding a cable. Someone pulling the other end of the cable. So you feel the 10 Newton there. But somehow there's another guy here pushing full. So therefore your total force you feel is actually they cancel each other a little bit. So you feel only 6. That's why N1 is 6 and N2 is 10. So that's kind of common sense you can use to judge. Okay. So the most reliable is don't use this common sense to get the values. It's just make a cut, draw the free body diagram, write it down. And that's the most reliable way of getting the solutions. All right. Because this part, I can tell you, most of the mistakes come from find out N1, N2. The other part is easy, right? You just apply the equation. Once you know N1, so you find the delta 1 will be N1, L1, E1, E1, actually the same. A1, right? A1 the same. Actually, you don't need the N1, so just A, right? Okay, now delta 2 will be N2, L2, and then E2, A2. They are the same. So that's the deformation part. Now, what's next? You just combine them. Okay, so your delta will equals to delta 1 plus delta 2. All right? A2, yeah, we assume that you have a uniform bar, right? I just want to make it easier. In reality, you can have A1, A2 different. Then you just put here A1, A2 to calculate. Yeah, I have like a uniform cable here, right? So uniform cable, if I'm putting a load here, this is master cable here, and then I use two hands pulling here, right? This is still the same uniform bar. I'm just applying two different loads onto it for this particular problem, right? Of course, I can apply two loads back to the previous problem, right? So if I have this one, let's see, okay, for this one, for example, this problem we just solved, you have A1, A2 there. I can also apply two loads there, right? So that would be another problem. Yeah, for this one, we just give you an example, just constant area, right? Okay, any questions for this one so far? Okay, what's the L1, what's the L2? L1 will be, okay, so this will be, actually I need to go back to this original drawing here. It's somehow just going backward. Okay, this is the original, okay, here's the original problem, right? So what's L1, what's L2? L1 is this one. So L1 is from A to B. That's L1. And then from B to C, that's L2. Because I'm dividing this segment into two different segments, right? So two segments. That's how I'm dividing at the point B. And each one we know it's uniform, so I have to divide two. Sometimes if it's more uniform, they have 3 loads there, then you have to divide to 3 segments. Right? Okay, then give you a quick quiz here, see how you divide it. Okay, let's say I have this situation. Okay, I have a bar. Okay, there is a hole here, right? And then I have another one load applying here. Maybe another load applying here. Then another load applying here. Okay, I have 3 loads. So P1, P2, P3. Now my question is, how many non-uniform segments do you have in this situation? Okay, let's say non-uniform, right? Anything non-uniform, A, E, or N, right? One of these 3 or combination will be non-uniform. Okay, now let's make a judgment. So first, this part is 1, right? This part is 1A. So these 2 A are different, so you have to divide them up. Okay, so you have 2 already. Now from here to here, the force may be different, so you have to divide again. So how many total? You have to divide into 4 segments, right? And then you calculate each one and add them together, right? So homework, you can have this type of problem, right? But for the exam, I may not give you this complicated. It will just take too long, right? So I may give you 2 forces possible, right? Maybe 3 segments. Because once you know the concept, it's just the same way. It just takes more time. Okay, now go back to this one. Okay, let me just make it easier. I'll redraw the first, the one we just did. So if we have this uniform bar here, oh, I'm drawing better. So P1 here, and then you have P2 here. Okay, same problem as before. Now, I want to make a little bit of change here. So I'll make a P1 equals to 10. All right? But I'll make P2 equals to, let's say, 16. All right? Now, if I ask you, what's the total elongation? How are you going to do it? It's the same, right? What we did, you divide it into 2 segments here, and then for each one, you find out what's the N1 here, what's the N2 here, right? So we can actually go back to what we already draw here. Okay, because I can change the color, so I use a different color here. So if we come back to this one, basically you draw N1, N2. Now, this value will be what? It will be 16, right? Okay, now what's changed? Oh, what will change in this case? For the blue one. Will the free body diagram change? No. Will the equation of equilibrium change? It's the same. Now, will the answer be different? Yes. So what's the new answer? What's the answer? You put it here. P2 is 16, 10, -6. Right? Okay, what does that mean? That means I guess wrong. It's now the tension there. So N1 should point the other way. It's compression. In other words, segment 1 will be under compression. Right? So you have basically N1 become a -6. Now if you put it here, delta 1 will be negative. So that means it's shrinkage. It's a negative elongation. So when you add these 2 together, what you get is actually they cancel each other a little bit. Right? So your total elongation can be a positive value or negative value, depending on N1 into delta 1, delta 2, relatively. All right. So the method doesn't change, but the answer can be different, depending on the magnitude of these two forces. All right. Okay, so here is another test. Let's give you another one. All right, so the same bar. Now I have this. Okay, so here is the P1 10 equals 10, this way. All right, now P2 equals 4. Okay, also this way. Now, what's the N1? What's the N2? How do you find it? Make a cut, right? Make a cut, draw free body diagram. Okay, so we have space here, so let's do it. Okay, so I'll make a cut, first one, and then I'll just draw this whole thing as free body. So I have P1 here, and then I have P2 here. Right? So then this will be N1 here. Now, what's the equation of equilibrium for this? Equation of equilibrium? Negative N1, negative P2, this is 2, right? Then negative P1 equals 0. Okay, so what's N1 then? Plug in. So what's the answer? Do you need a calculator? Anyone need a calculator for this? Okay. If you're not sure, you can use a calculator. That's fine, but that just slow you down, right? Okay, so what's N1? Negative 14 Newton. All right? So you can see here, someone here is like two of you stand there, right? Someone is pushing this way, and someone is pushing in the middle. So whoever at the end will feel both the pushing add together, because they're all the same direction. So they add up. So therefore, N1 is bigger, negative 14. Now, what about N2? You need to draw another free body diagram, right? So this will be P1 here, and this will be the N2 you're looking for. Actually, it's a 2. I'll somehow write it. Okay, now equation of equilibrium. Negative N2. Okay, so will be negative N2, negative P1 equals 0. So what's N1? What's N2? Negative 10. So here is compression 10 again. Right? Okay, so when you go home, here, this bar, okay, keep changing the direction. All combinations. Put both this way, both the other way. One this way, one other way. One this way, one other way. Keep all these combinations. See if you can find N1 and N2. If you can do all that, then you will be very confident to find all these internal forces. Yes?
Your free body diagram there, you have N1 going to the left. If you flip that, had it going back into the bar,
yeah.
You have N1 equals 4 to the positive 14.
Well, if I know it's compression, so I can, let me just use a different.
Assume, I guess, N1 went out, or could you assume because P1 and P2 are going to the left,
yeah.
N1 needs to
Yeah, so in this case, if I don't want to make any judgment, any assumption, I'll just always put a positive stretch. That will be the one I put there. But somehow, based on this situation, I know if you are keep pushing, then this will be compression, right? That's kind of common. So I kind of judge, okay, this should be this way. So I will say, I label N1 should be this way. That's fine. But as long as you stick to it, whatever your judgment, you put it there, don't change in the middle of this solution process. Keep it that way. Okay, what if you use this one? Then you will find out, let me just write down here. So you will find out N1 will be equal to positive 14, right? Okay, now, what do you do with next step? Okay, so let me write down what you do with the red solution. Okay, so for this one, you calculate delta 1 will equal to N1, L1, E1, and A1. Okay, this will give you what? A positive value, right? But what does this positive value mean? It means that you compress this much, right? Now, if I'm not using this one, I use a blue one. So I calculate delta 1. Actually, it should be blue, so here. So I calculate delta 1 equal to N1, L1, E1, A1. Okay, if I calculate, use this equation, now I put N1 equals negative 14 there. So I get a negative value. What's that mean? That means I assume elongation is positive, so now negative value means shrinkage. Okay, so this is perfectly fine. However, when you put into your next step, okay, you're going to calculate delta equals delta 1 plus delta 2, right? If you use a blue assumption, right? Okay, so that you just calculate that way. Now, what if you use the red? You assume this force was this way. What's the total elongation? You should calculate. Okay, let me change it to red. So you should have delta will equal to delta 2 minus delta 1. Because you know delta 1 is a shrinkage. So your final summation will be different if you use the blue approach or use the red approach. This should actually give you the same number. So you prejudge, okay, this is compression, then you always use compression, shrinkage, go down. Or I don't care, I don't make judge call, I just use everything, just put together, then whatever positive, negative, I just put them together. Okay, either way is fine, but don't switch in the middle of your solution. Then you can get it wrong. All right? Okay, any other questions? Okay, any other questions? All right, let me give you one problem that you can think about before you go home. So here is one. Here's my last example. What happened? Let's come up with the shade. One here. I don't know which one I keep. Let's say escape. Click on this again. Well, anyway, go ahead. Draw it here. So this is the wall. This may be hard. Okay, so I don't know which one what I hit it. So I go backward, back. Cancel all this. Okay, now let's see if it works now. Okay, back to normal. So let's insert a page. Okay, so I want to end with this example so you can think about it. Go back here, and this is the pen. So we have this problem. So you have a bar, all right? So that's between two walls. Okay, now I have a load I'm applying here, say P1 equals 10. Okay. Now it's like you have a rubber band between two walls. Now you're applying a load in the middle, right? I think I have my rubber band somewhere there. Okay, so you're applying load in the middle. Now my question is, when you're applying this load in the middle, what's going to happen? This is our rubber band, right? Soft band, deformable band. So this point, let's call this one point A, B, and point C. So you're going to push, point C going to move, right? C going to move to the right. That kind of, you can sense it, right? Okay, now the question is, point C, how much is going to move? We know point A, point B are not going to move because rigid wall there. We assume the rigid wall. Okay, how can we find out the elongation or the movement of point C? What kind of situation we have? Non-uniform bar, right? Okay, so non-uniform bar. Therefore, we need divided up. So the logical dividing point will be here. Let me use it. This part, C. Okay, if I divide up, so I need to find out what's the N1 here what's the N2 here? Right? Okay, so we need to draw a free body diagram. So let's draw a free body diagram. So you have N1 here. All right, so you have this one. Actually, I need to change to black. Oh. All right. Okay, so black. So this one, I just draw this whole thing here. So this is the wall here. All right. Now, N1 will be here. Okay, I need to label all the forces. So I'm going to have point C, you have a load P1 here. Now, what's here at point B? You're going to have a reaction, right? Can be left or right. If I don't know, I can just assume any direction. So how about I assume it will be which way? To the left or to the right? To the left. Okay, so I'll go to the left. All right, so you're going to have this, we call it R, at the point B, so RB. Okay, this is a free body diagram, complete. Now, for this one, okay, now if I want to find the N2, so I can draw here, right? So N2 will be this way. So this will be N2, and now this will be R here. RB, actually, right? Okay, now write out the equation of equilibrium. So this one, you have negative N1 plus P1, then minus RB equals 0. This one gave me N2 negative RB equals 0. Okay, now can I find out N1, N2 from here? You need the R, RB actually, right? Now I don't know RB. Can I find out RB? Equation of equilibrium. Now I have to draw this whole thing. So I draw this whole thing here, right? So you have RB here, and then you have load P1 here. Now you have a load, maybe a RA here, right? Now I can write the equation. So negative RA, negative RB plus P1 equals 0. Now can I find out RB? No, because now RA come in. Okay, so I have to, maybe I can draw another one. So I can draw, okay, so I can draw this part, right? So this will be N1, this will be RA. But that's related RA to N1. So it doesn't help, right? So I can also draw this one. Cut here. So I use the two cuts. So here is P1. So here will be my N1, and here is N2. And this one actually gave me negative N1, negative N2, and plus P1 equals 0. Oh, I'm drawing the, sorry, should be which one? So negative N1, so N2 is positive. Good catch. Yeah. Right? Okay, now can you solve the N1, N2? Well, basically, I have two segments, right? AB is a segment. AC is a segment. CB is a segment. So I have N1 in this segment, N2 in this segment. Can I find out from all these equations? The answer is no, although I wrote already 5 equations there. Why? Because when you have this problem here, how many equations you can write? Independent equations. Only sigma fx equals 0. One equation in principle, right? And you have 2 unknowns, so you cannot find it, right? So we call this kind of problem indeterminate problem. Okay, so here is what we're going to talk about next class, indeterminate problem. Okay, this actually is the most exciting part of this class. So make all effort to come Monday. All right? Most difficult part as well. Okay, you have a question there?